Hello, my name is Steven Sims, and wanted to put a quick video together for the Off by One security channel on format string vulnerabilities and exploitation. I got this request a couple of times recently. I was doing a stream and started to dabble a little bit into demonstrating some format string stuff on Linux. And the questions come up a lot over the years around how can you still potentially abuse them if you do find a vulnerability. Historically, the best case scenario for an attacker would be on an operating system that supports the %n identifier. What that one allows you to do is it takes the number of bytes in the print statement and it writes it to a address or pointer that you provide. I'm not sure what purpose that ever served, but since that was a possibility, it would open up the opportunity for what's called a write what where primitive, where you would be able to write any value to any location in memory that's writable. And a common technique that we would use, and actually I wrote a exploit against Wireshark vulnerability a long time ago. It was actually a end day exploitation where the vulnerability was published, but there was no working exploit or any details about it. And a particular company that I was working with desired to have a working exploit for that particular vulnerability. And so I was able to weaponize it. And since it affected Wireshark, it was actually one of the packet parsers Wireshark or sniffers in general have to run as root or administrator or system, which means that if you can exploit a vulnerability, of course, you're going to run under the context of root in that case. And that one in particular supported the %n identifier, which allowed us to get a write what where. And what we would typically overwrite is some table of pointers, for example, the global offset table, if it's writable, or something like detours that you could gain control that way when a program goes or process goes to exit. So it's a very powerful specifier or operator, whatever you want to call it. But that one, I don't believe it was ever supported on Windows. If it was, it must have been a long time ago. Most compilers nowadays, that they're going to complain to you. They're going to say, hey, it's missing a format string, or maybe even try to correct it for you. But you do still come across them. And nowadays, when you come across them, what you can use them for potentially is something like an information leak, if possible. It depends, obviously, on many different factors, but we're going to look at an example today. I decided that we'll take a look at the Windows sort application vulnerability that was there for decades. It was a 32-bit version of sort, I think all the way up to certain versions of Windows 10 that it was still, in fact, vulnerable on. And Microsoft knew about this, of course, and they never patched it. And I just want to hopefully demonstrate that with something like that, could we potentially leak out an address of a DLL and then calculate the relative offset, and of course be able to build a ROP chain or something like that using the relative virtual address offsets. So that's my goal. I'm not saying that you could use that specific vulnerability, but just the in theory, if you do come across one, you might be able to leak something out like stack canary values, or leak out something else that's sensitive from a process, or maybe even calculate the base address of a DLL on a Windows system or on a shared object on Linux. So the very first thing we're going to do here is just look at a simple Linux example. This is going to be from a little proof of concept, capture the flag binary, and we'll just see what the vulnerability is and what you could potentially do with it. First off, though, you can see here, I'm just going to a website, c++.com, and this shows you all the different format specifiers or identifiers that you can use in format strings. And the purpose of format strings, for the most part, is to allow a developer to specify how they want data printed to a screen or written to a file, or one of several other options. And the printf family is actually a family of functions. You've got sprintf and a bunch of others out there. But you can see some examples here on the screen. We've got like %x. If we use that, it's going to give you hexadecimal value. If you use s, it's going to give you a string of characters. That one in particular expects for you to provide it with a pointer. It will go to that address and it will write to the screen, in this case, whatever's there as if it's ASCII text. So you might be able to leak something out. %n, you can see down here at the bottom, that's the dangerous one, the one that allows you to potentially get a write what where opportunity that would obviously be the most lucrative or valuable to you if you came across that. So let's go to a quick example here. And the little program here is just called FMT1, format one. And first, let's look at the source code, very simple source code. And the vulnerability in this particular one is right here, obviously. In the first printf statement, you can see there is a format specifier. In the second one, there is not. And what happens is if it's missing a format string specifier or whatever, then if the person using the application can somehow, uh, if in a print statement it's taking in user input either from a file or from the command line or wherever, they could then substitute and put in their own format specifier, and the printf function call will actually take that as a proper identifier as if it were in the code to begin with, which is where the problem comes in. And it's really easy to miss format string bugs if you accidentally compile one into a program. And it's easy to miss that there is a vulnerability if you're just using a program, because the program still seems to act normal. It just prints out whatever's there as a string if it's missing the format specifier. But if you're going to check to see if there's a vulnerability, then you'll see some clear indication as to that vulnerability being present. And then it's also, of course, easy to fix it. If you do find that vulnerability, you could just go into source code and add that in. Again, we'll look at a Microsoft example in a moment, but let's run this little program. So if we say FMT1, I'm just going to put in 4 A's. And you can say it prints out the statements here with the format identifier. You typed AAAA. Without one, you typed AAAA. So even though that bottom one's missing the specifier or identifier, we don't see any indication that that's the case. Down here at the bottom is just some kind of little data that allows you to see what you're doing when you try to actually do a write what where attack with the %n identifier. It's saying 5 times 5 equals 25, which we know that's true. And it's saying that the address of that variable 25 is stored at this static memory address. So we're not dealing with ASLR right now, but on the Windows example, we will be. So if in theory, we were able to exploit the write what where primitive or opportunity with the %n identifier, we now have an address of something where if we were to then write to that address, it will change this value hex 19, which of course is hexadecimal or base 16 for the integer or decimal value 25. So that's kind of going to be our goal. But the very first thing we're going to do is just see if there's a vulnerability here to begin with. So we'll run the same command as before, but this time we're going to say %x, %x, %x. And you can see when we do that on the bottom here, instead of printing out the %x's like it does on the top, it's printing out what looks to be memory addressing. And so it's just grabbing from the stack, in this case, double words, and just printing them to the screen one at a time. And each time we add another %x, it jumps to the next double word on the stack and it prints that out to memory. So let's try it again. I'm going to make it a little easier to read. We'll say %x dot %x dot %x, and we'll just keep going a little bit and see if we get anything more. So now you can see the separation, the little decimal point in between what's being printed off the stack. What I'm looking for is, since we're printing values off the stack, my AAAA should be there somewhere for this printf call. When we call the printf, then on the stack, in this case for 32 bits, since we're using the base pointer, our argument to printf is going to be on the stack somewhere. So if we keep putting %x, eventually we'll see 41414141, which of course is an ASCII capital A. So let's add a couple more in. And still nothing, so we'll do it again. And in this case, when we put 9 of, or is it 9, 1, 2, 3, 4, 5, 6, yeah, 9 of them, we can see 41414141 at the end there. So we know that we've reached our argument, our value that printf is printing to the screen. So what does this mean to us? Well, that's with the %x identifier, which just dumps out in hexadecimal what's there. If we change this to a %s, then what it's actually going to do is grab 41414141, and it's going to treat it as a memory address that it wants to go to and grab the contents there and print them to the screen. So if we change this %x on the end to %s, it's going to have a segmentation fault. And there you can see a seg fault happen. The segmentation fault, of course, happened because that address is not mapped. There is no 41414141 mapped from virtual to physical memory. So, okay, great. Well, what if we can find something, an address that's inside the application itself or inside the process itself that is legitimate? So there is something there. Well, we could try to guess, like since ASLR is not on, we could try to guess an address like 804.82.0.0.0. And let's try that. So in this case, we're going to use Python here. I'm going to say backtick Python -c for command prompt here. I'll change it to 3, even though it doesn't matter. And we'll say print. And now we're going to put the address that we want something to be printed from in a little endian format. So reverse order, because it's x86. So we'll say /x. And I'm going to put, how about 08? So 804, 84, or 8208. So 820408. Now that is the address I want to print from. And then we'll put our format specifiers in there like we already have them. So when we do this, it says segfault core dump. So nothing is at that address, 804.8208. Nothing's at that address for it to print out. If I don't get lucky here pretty soon, we'll actually go and debug and get an address that's real so we can see if we can print something out. So I'll put 88. Same thing. We're just getting crashes here. So let's try 83. 80. Yeah, let's just go in so we're not wasting time here. So I'm going to say GDB FMT1, and I'm simply going to say x/8s, so examine 8 strings starting at this address, 804.8200. All right, so here you can see some strings that are inside the program itself. We see gmon start and we see libc.so.6. So if we use that address right there, I was pretty close. I did 804.8208. If I would have done 18, we probably would have leaked that string out. So let's try that and see if it works. So now we change that address to 804.8218. And we do that and we don't get the result I'm looking for. Let me just check my syntax here again real quickly. So formatting Python -c print 804.8218. And then we've got our format specifiers. Let me try removing those decimal points to see if they're causing an issue. And no, that doesn't seem to be doing it. We're doing something small here. Let me just change it to Python instead of Python 3. And not that that's going to work, but and for some reason it did work. Okay, whatever. I'm not going to worry about why. But when we do it now, we can see that we leaked out the string libc.so.6. So great. We know what we can do now with the power of a format string vulnerability and the %s identifier. We can print things out from inside the process that we shouldn't be able to print out like that. So in theory, if there was something sensitive in memory somewhere and we guessed the right address, it would print that out to the screen. And that could be possibly useful. Like I said, maybe you can. Now, this would require, if we're doing something like stack canaries and it's a random canary that's being used once per process invocation, when we do this, if it caused a seg fault and crashed the program, well, that's not going to be very useful because if we start the program again, then it's going to be a different canary that's used. But if for whatever reason we can actually do this and the program doesn't crash, then we could potentially do something like a canary bypass in theory. But that's just an idea. Now, let me show you a quick example of the write what where opportunity if the %n operator identifier is supported. So I'm going to go ahead and change %n to, or %s to %n, and we're going to change this address to the one on the screen that is the address where the hexadecimal 19 is located. So 804.970C. So let's change that to 970C. And look what happened. It changed from 19 to 2F. So that proves that we were able to write something to an address in memory that is writable. This, in this example, it's in the data segment, which is typically writable. So what the value then would be if we can actually control what is being written to that address, then we can get that write what where opportunity and write something meaningful to the destination. So with basic format string exploitation with %n identifier, you can typically write 2 bytes at one time. I'm going to break it into single bytes at a time just to make it more methodical here as we go through it. But our goal is going to be to write dead code in hexadecimal to that location. So let's give that a shot real quickly. To get started here, and remember what %n does. It takes the number of bytes in the format string, or not in the format string, but in the printf statement, and writes that number of bytes to the destination. There's a cool trick you can do, though, where you can use a length operator. And for example, look where I'm at with the %x right there. If I add a value like 180 in there, watch what happens to the address or what's stored at that address. See how it's E2 now? So it literally took whatever value I put there, and it includes that number of bytes into the count for the number of bytes in the print statement. So it's a very powerful way for us to be able to specify what we want to be written to that location. So if we want this to be dead code, we want DE to be there at the end. Well, I'm pretty close to that, I guess pretty close. So like if I basically just subtract and go down to 160, or I meant 160, sorry, 160. Now we're CE, so we're really close. So if we say 170, we got D8. So how about 174 or 6? And there's DE. So 176 bytes added as a length to the format or to this printf statement using that operator. We are able to control the precise number of bytes so that what's written to the address of our choice is what we want to be there. Now, the cool thing is we can actually write multiple bytes at the same time if we take advantage of the way this whole thing works. So the first thing I'm going to do is I'm going to get rid of that width or length that I put in there, and we're going to set this up. And in order to do that, we need to then put in 4 bytes of padding. I'm just going to use the word pad. And then we write the next address we want to write to. So the first address we wanted to write to was this one, the 970C. So the next one's going to be 970D, and then the next one 0E, and then 0F. And then we're writing to 1 byte at a time to take the whole double word. And it works great. Why do I need to put the pad in between the addresses? Because in order to use that width operator and add that number like you saw me do, we need to have a %x to do that with, and then a %n for the actual write to that location. So it's really weird the way it works, but it's just the way it works. So I'm going to take this address and we're going to write it 3 more times. And I'll have to fix it, of course, but let's put that in, paste. And then we're going to go back and change that byte to 0D because that's the next byte over. And then we're going to put 4 bytes of padding in. So I'll just put PADD. You can put whatever you want in there. And then we'll paste that in again. We'll change this one to 0E. And then 4 bytes of padding. And then finally, we're going to paste in and put in 0F. So again, we've got C, D, E, F. That's each byte that corresponds here. That would be C, that would be D, E, F. The padding is because we're going to have to put a new %x operator in to be able to utilize that width or length option. So if we do this just that way, because we increase the number of bytes in the print statement, obviously that value changes here. So now we got to recalculate again and figure out how many bytes we need to add to change that to DE. You can use a calculator and do it really quickly. I'll actually show you a trick here in a moment. But let's figure that out. I'm going to say 140 and see what we get. So we got D2. We got really close. So how about 149? Really close. So DB 151, DD 152. So 152 gets us DE. Now what we need to do is add another %x followed by a %n. Remember, this new %x is what corresponds to this pad right there. And then the new %n is the address we're going to write to. So we're going to use and figure out the width value or length value we want to use. So let me calculate this. So we know that DE is what we have already with the length that we're using. So we can do some basic math. I'm just going to say Python minus C, and then print. We'll do 0x, what we want to put there, we're writing dead code. So C0 is what we want. DE is what's already there. So we need to subtract DE from C0. Well, that's going to be a negative value. So I need to add a 1 in front of the C0. So we'll say 1 C0 minus 0x DE. And again, if that doesn't make sense, remember, we already know that we're getting DE at that location based on that length we're putting there of 152, right? So what we're doing is, what do I want to write into this byte position? I want C0 to spell code. So I'm going to take C0 and subtract from it DE, but that would be a negative value. So we're putting a 1 in front, and that should give us the value 226 here. So watch what happens now when we say 226x. We get code. So it worked out nicely, right? Now we have 2 bytes. And then we're going to move to the next one. So to do that, let's do the same calculation, but we'll subtract from C0, or we'll subtract C0 from 1AD, because we want the AD part of dead. And we get 237. So we'll say percent 237x percent n. And there we've got AD code. So only one more to go. So we'll say subtract AD from DE. That won't be a negative, so we can just leave it that without the 1. And then we put in our final one, percent 49x percent n. And now we've got dead code. So that's the full write, what, where in a single Python line, right? We can do multiple writes with the same format string magic, which is pretty cool. Now, that's fine, but what would we really want to overwrite? Well, like I said earlier, we'd want to write something like the address of something in the global offset table. So we could do that and say obj dump minus capital R for relocation entries. This will show us the global offset table, which if you're not familiar with that, it's used for symbol resolution. And we'll say FMT1. So this is the global offset table jump slot for the printf function. And basically the way linking works, and I've gone through this previously on the channel, I've done a video on this kind of stuff. Basically how it works is when you call printf the first time, if lazy linking's being used, then it's going to actually go to the procedure linkage table entry for printf, which has a jump to the address in the corresponding entry for printf in the global offset table. And the very first time we do that, it's not yet been linked. So therefore, it's got to call the dynamic linker. It's got to go get the real address of printf and write it to the global offset table. And then going forward, anytime printf is called, it doesn't have to do that linking or lookup again. It'll just go to the right address. So if we hijack that, if we overwrite printf's entry in the global offset table, the next time it's called, it will call our address. So our goal is going to be to write dead code to the global offset table entry for printf. And I'll just show you this real quickly in the debugger. So we'll grab our input here as is, copy that. We're going to go into the debugger. And if we just paste this in now as is and just hit enter, it's the same thing we saw before. Dead code, we wrote it to that location, process exits normally, everybody's happy. But now let's change that to the global offset table entry for printf. So to get that real quickly again, I'll just say shell obj dump minus R for relocation, and then FMT1. There's the address that we want to use right there. So instead of using that address of the variable where 25 was located, we're going to use that address that I'm highlighted. So 804.96F8. So 6F8. Actually, this needs to be the last address because little Indian. So it'd be F8 9AB. So we change that to B, and then this will be 96FA. This will be 96F9, and this will be 96F8. If I did this correctly, we should have the instruction pointer go to dead code. And there we are. You can see right there, if we say info reg EIP, we got control of the instruction pointer via the format string vulnerability. So that's great, pretty cool, right? But that's old, and %n just isn't really supported in many places anymore. So I'd be extremely surprised if you came across a system, unless it's old, that you would be able to do something like this. It's definitely possible, but let's move on to something that is more likely going to be how you could use it today if you can, in fact, use it. So I'm going to go ahead and jump over to this Windows VM right here, and we're going to bring up the sort program. So this is going to be the sort vulnerability that's existed ever since the dawn of Windows, all the way up to like Windows 10 at some point for 32-bit only. And I don't know why it's been reported. It had been reported many times over the years to Microsoft, but they just didn't patch it. So first off, sort is a basic little program. If we just say CMD and I go to my desktop here where I've got sort, I'll just say sort AAAA. And you can see it says AAAA, the system cannot find a file specified. So once you give it a file so it can sort it, right? I don't have a file called AAAA. Same thing as before. If we say %X, we just saw that on the Linux side. See how that memory is dumping out here? So pretty interesting. And just like before, we want to find the offset that corresponds to our argument. So let's do that. We don't see it yet. Still don't see it. And there it is. So that's the seventh argument ends up being our A's on the stack. So just like before, we've got control over that position. So if we change this to %S, you could see it crashes the sort program because that's a segmentation fault. What we're going to want to do is see if we can leak something useful out that might allow us to figure out with ASLR on what the base address of a DLL is. Let's see if we can figure that out. First off, though, let's go to sort and figure out where the vulnerability is. So I'm going to use a script that I wrote a long time ago called banned functions. It basically just takes all the Microsoft identified unsafe C functions or C++ functions, and it checks your code base to see if you are using those banned functions. So real quickly, I'm just going to run that script right there. And you can see the only banned function that it finds is printf, fprintf, in fact. So, okay, great. We've got fprintf. We know that that must be the vulnerability, right? Because we saw the vulnerability literally in front of us just a moment ago in command line. So it has to be that call. Now, if there were other banned functions like stir copy and stuff like that, those would show up too. And you'd be surprised. Like if you were to go and load into IDA MMC, the Microsoft Management Console, where you can like load GPOs and stuff, and you ran that banned function scripts, it uses stir copy, the default basic old stir copy. Doesn't mean it's vulnerable, but stir copy is not a great choice. And if the user is able to, of course, influence it somehow, they could potentially cause a buffer overflow. So in this case, we're looking here. Now, the cool thing that this script does is it sets breakpoints automatically for you on every call to the function that's banned. So we can actually just double click on these addresses like that, and it takes us to the location where those calls are at. Now you can see here in this function that the printf statement or the printf call, this one has a format string. So does this one. So those two won't be vulnerable. But let's go and look at a different one. This one here, there is no format string. And in fact, there's two calls to printf in this function, and neither one of them has a format string. So there's a good chance that this is where our problem is. So what I'm going to do is I'm going to run that script again to disable all the breakpoints, and I'm just going to set it on those two function calls. So we'll say script file, ban functions. If you run the script again, it turns off all the breakpoints. So now I'm going to go back here, and we're going to set up breakpoints on the two calls to printf. So here's the first one, and we'll just set a breakpoint there, and we'll go to the bottom one, and we'll set a breakpoint there. And then we're going to go into our debugger settings. We'll choose local Windows debugger. We'll go and set our process options, and we're going to put in the AAAA %X. Let me think about this for a second. So I'm thinking about what I want to do here. I want to figure out how we can use this to be useful. Let's just see it pause and just verify first. So I'm going to put BBBB and we'll %X dot %, actually no dots, X, percent X, percent X, percent X, percent X, percent X. That's 1, 2, 3, 4, 5, 6, 7. I think that's 7. So we'll say OK. And now when we run the process, we should break at that location. So now we've hit our breakpoint. In the background, this is the sort window that's being debugged right now, but we haven't made it anywhere yet. So nothing's been printed to the screen. And you can see in this first one, if we look at the stack arguments, like right there, that's going to be the argument on the stack to this printf call. And let's see what's there. We'll just dump it to the hex window. And you can see that's our BBBB. So that address is the argument for the BBBB. Okay, great. So let's step over that one. So we'll say debugger, step over. And now let's look at our background window. Now you can see that it printed out our data as well as the 42424242, but we didn't get that message yet that says there's some error. That must be in the next call to printf. So if we say play now, we hit the next call to printf, we look at the background, it still hasn't printed the error message. And if we step over this, we can see right now automatically that argument location says the system cannot find the file specified right there. So if we step over this one, you'll see in the background, now that error message has been printed. So we know exactly where the bug is. So if you were going to go fix this problem, you know where it is, you can go fix it. But what we want to do is see if we leak out anything useful. Now, if I remember correctly on this one, the very first value that's printed out right there, that address, it is an address. I think that that's inside of NTDLL. Now, if that's inside of NTDLL, here's the cool trick. ASLR is on Windows 10 and Windows 11, right? Can't turn it off. So if we wanted to find the base address of NTDLL on this system, and remember on Windows, the DLLs only get rebased once per boot. So if you were exploiting a Windows box and you needed to know the address of a DLL so that you could like do a ROP chain and learn all the relative offsets, you would be able to abuse something like this to potentially get that information. But let's see if we can get it working. The address is 77009C40. So I'm going to copy that address. I'm going to go back to the debugger and let's look at the loaded modules. NTDLL is 773D. In fact, let me switch this over to WinDebug because I don't remember all the commands in IDA's debugger to do some of the things I want. I think this guy's got WinDebug on it. So let's kill this process here. And let's see if we get WinDebug. Hopefully it just comes up and we don't have any issue. Okay, here we go. So we got WinDebug up. Now let's go and open up sort. So launch executable. Let's go to our desktop and grab sort. Okay, now we've got that in the debugger. So that address we have is still in my clipboard. So I'm going to paste it in here. That's the address, right? So if I say ln on that address, it says exact matches kernel 32. So it's not NTDLL, it's inside kernel 32, it looks like. So it is something, and it's an exact match, which is always good because that means something literally is at that precise address location. So if we look at the base address for kernel 32 then, since that's the DLL we're leaking, it is at 770D0000, right? 770D0000. Let me just validate something. 76. No, it's 76FF00. That's going to be the end. So 76FF0000. So if we subtract the base address, the load address for kernel 32 from this address that we just gave it, that should be the relative offset of this thing, right? This whatever is being leaked out. So let's get the calculator up real quick. And I'm going to paste. Oh, it's not taking it. Let me check the hexadecimal, paste that in, and we're going to from it subtract the base address that's up on the screen for kernel 32. That's 76FF0000. So 19C40 should be the relative offset. Now, how do we validate that this actually works? What we're going to do is we're going to grab that value, 19C40. I'm going to go to my Linux box just to paste it in here. Let's see if it takes it. All right, there's that value. I just want to store it somewhere because we're going to reboot that other VM real quick. So to prove that this works, we're going to reboot. No, I didn't do it. Nope, hold on. I accidentally paused the VM instead of rebooting. It's a wrong option. So let's go ahead and close this stuff out, and then we're going to quickly reboot. That's an ugly desktop, I know. Restart. And then when that restarts, we're going to run the sort vulnerability and do the calculation and see if it's right. If it's right, then that would be a working relative virtual address offset that we know we can always subtract from this vulnerability to calculate the DLL base address. And then you can obviously write your ROP chain because you've got the base address and you can add all the relative offsets to it, and it would be working. All right, let's go back in, bring up a command shell, and go to my desktop. And we're going to say sort AAAA %X, %X, %X. 1, 2, 3, 4, 5, 6, 7. I didn't need to do all that. All I need is this first one, actually. Yeah, let me just clear the screen and do that. It's going to be cleaner. So let's just do 1. And that very first thing we leak here should be that same variable from kernel32.dll. So what we're going to do now is bring up a calculator again. And we're going to go to hexadecimal. We are going to take that leaked address and paste it in. And we're going to subtract from it that relative virtual address that we had, which is 19C40, 19C40. So minus 19C40. And I'm crossing my fingers now. That looks pretty good, doesn't it? 7751000. And let's go into WinDebug real quick. And let's see if that is the base address for kernel 32. So let's just simply open up sort again. And we should see it right at the beginning here. So right there, kernel 32. What do we have again? We've got 77510000, 77510000. So perfect, it worked. So hopefully that explains or shows you an example as to how a format string bug could still potentially be useful, because this would be a memory disclosure, information disclosure bug that we could then use to learn about the base address. I'm not saying it's going to yield you lots of profit or anything, but it's just the concept behind it, the types of things that you can do with this type of bug. So hopefully that was useful to you. If you have any questions or comments or anything, please post them, all that good stuff. And thanks. We will see you next time.